If you're a baseball fan, you might know that the Baltimore Orioles probably don't follow the Baltimore Orioles because nobody really who's sane would follow the Baltimore Orioles, but the Baltimore Orioles have been doing pretty well lately. In the last 10 games, they're 7-3. 7 wins, 3 losses in the last 10 games, as of yesterday, that is. I want to know what the Baltimore Orioles, who are 7-3 in their last 10 games, and this train barreling down the tracks have in common with each other. Just give it a little bit of thought. Think outside the box. Don't think too literal. Think more figurative. Cameron? Yeah. Look, they're hard to stop. They're both hard to stop, right? When you got a baseball team or a hockey team or any other team that's on a bit of a winning streak, it's kind of hard to stop them. And a train rolling down the track is hard to stop as well. So there's one word that we usually use to describe how hard something is to stop. It means two different things when we're talking about a baseball team versus a train, but it's the same word. Momentum. They both have momentum. This is more psychological momentum, right? A baseball team that's on a winning streak, it's hard to beat them, it's hard to stop them, not because they're physically any better than they were 2 weeks ago, but because psychologically they're on a roll, and you know psychologically it's hard to beat that team that's on a roll. This is more physical momentum, how hard it is to stop something. We're going to focus, obviously, in this unit in Physics 30 on real momentum, on physical momentum, as opposed to this psychological momentum. I'm going to define momentum first, figuratively, as how hard it is to stop something. Notice I put that in quotation marks, because if I ever asked you to really define momentum, it would not be how hard it is to stop something. That's just how we're going to understand momentum. The real technical definition comes from that. What is it that makes something physically, that is? We're not talking about the baseball team momentum anymore. What is it that physically makes something difficult to stop? There's two factors. Hey, what's one of them? Kessler, what's one of those factors? Okay. Kessler said inertia. What's inertia related to? Anybody remember from Physics 20? No, it's not related to velocity. It's related to mass. Inertia is related to mass. So the heavier something is, the harder it is to stop, right? That's why a train has a lot of momentum. That's why it's hard to stop, because it has a lot of mass. What's the other thing that makes something hard to stop, even if it's not as heavy as a train, Spencer? Speed or velocity, right? We think of momentum and inertia often as being the same thing. They're not. Inertia depends upon only mass. Momentum depends upon mass and velocity. We're going to say momentum is the product of an object's mass and velocity. That's its real definition, which comes from our understanding of momentum, which is how hard it is to stop something. Now we're going to compare that to inertia, which you learn in Physics 20 is the tendency of an object to, careful here, to resist a change in motion. What do I mean by that? Well, if an object is moving, what's it want to do? Keep moving. It doesn't want to change its motion. If an object is at rest, it wants to stay at rest. It wants to keep doing what it's doing. So in order to have momentum, you got to be moving, and we measure how hard it is to stop the thing that's moving. In order to have inertia, it doesn't have to be moving at all. It just has to have mass. The more mass it has, the harder it is to stop it if it's moving, but it's the harder it is to start it if it's not moving. Do you understand the difference here between momentum and inertia? How hard it is to stop something that's already moving. Inertia, how hard it is to start something that's not moving, or stop something, or slow down something, or speed up something that is moving. Momentum depends upon mass and velocity, and inertia depends only upon mass. So I got two trains now. One train is sitting at the station at rest. One train is moving down the tracks. I don't know how fast it's moving down the tracks, but it's moving down the tracks. I want you to answer the following questions for me. train number one, sitting at the station, does it have inertia? Does it have inertia, Spencer? Yes, it does. Why? Because it has mass, right? Does it have momentum? Matt? No, it doesn't have momentum. Matt, why doesn't it have momentum? Because it's not moving. It still has mass, but it needs mass and velocity to have momentum. So it does have inertia. It does not have momentum. What about the second train that's moving down the tracks? Does it have inertia? Yes, it does. Why? Because it has mass. What about because it has velocity? Doesn't make any difference, right? Its velocity doesn't make any difference in terms of inertia. But it has inertia simply because it has mass. What about momentum? Yes, has a lot of momentum. Why does it have a lot of momentum? Primarily, probably because of its mass. But it has momentum because no matter how heavy it is, though, it's not going to have any momentum if it doesn't have that velocity to go along with it. Even if it's just a little bit of velocity, it can still have a lot of momentum because of its mass. Okay, does that make sense? All right, I want you to refer to your data sheet for a second, the sheet that I handed out to you at the beginning of class. Scroll down to the bottom left-hand corner under the category of momentum and energy. The very first equation that we see there is our equation for momentum, our first new equation in Physics 30. Momentum, given by the symbol P. Go ahead and ask me why we use the symbol P for momentum. I don't know. I don't know why we use the symbol P for momentum. You'd think it would be like M or something, right? But there you go, it's mass, so we got to come up with a new letter. I don't know. But it's P. It's P with an arrow over it. What does that arrow tell me? That it's a vector that has direction associated with it. P is momentum. That's a lowercase p, by the way. If it was a capital P, it would be power. Power or pressure. It could be pressure. Okay, although we don't, in Physics 20 or Physics 30, we don't talk about pressure, but yes, it could be. M stands for mass, because of course it's dependent upon mass. And the units for mass would be kilograms, yeah. And V stands for, not the speed, but the velocity, because direction matters. The units would be meters per second. Anybody want to take a stab at what the units for momentum would be? Oh, you're so close. Not meters per second per kilogram. You're probably thinking the right thing, just not saying it right, actually. Kilograms times meters per second. All right, it's M times V, kilograms times meters per second. $114 on the first day of Physics 30, and already we have our first example. Example number one, which is, I would say, probably the second easiest example that you're going to see in Physics 30 all year. There's one later on in our electricity unit that's like ridiculously easy. But this is pretty straightforward as well. This one says a 145-gram baseball, which is the actual mass, give or take, of a baseball, is traveling to the west with a velocity of 90 kilometers per hour. Determine the momentum of the baseball. Well, what do we have given to us here? We got a mass of a baseball is 145 grams. We have a velocity is of 90 kilometers per hour. And we want to find momentum. And we know that momentum is simply m times v. That's the definition of momentum, right? The product of mass and velocity. Multiply them together, right? Well, there is one thing we got to be careful of, and what is it? Nick? Yeah, it's in kilometers per hour. So we're going to convert this to meters per second. Who remembers how to do that? Yeah, we can times it by 1,000 to get 90,000 meters per hour, and then divide by 3,600 to get 90,000 meters divided by 3,600 seconds. But that ends up being the same thing as dividing by 3.6. So there is a little shortcut, which I didn't teach you in Physics 20 because I wanted you to know how to do it. But now, I think you're smart enough to take the shortcut now. Divide by 3.6. When you do that, you end up getting, 25.0 meters per second. All right, so we're set to go now, right? Well, not really. There's one more thing that I got to watch out for. Yeah, we got to go kilograms as well. We divide by 1,000 to get kilograms. That becomes 0.145 kilograms. So now we're going to say 0.145 kilograms times a velocity of 25.0 meters per second. When we do that, we end up getting 3.63 kilograms meters per second. Now, a couple of things that I want to draw attention to here, okay? Question? Yes, that was one of the things that I want to draw attention to. Thank you, though, Quinn. The first thing that I want to draw attention to was significant figures. Okay, this is correct for significant figures, 3 digits. Why did I go 3 digits? Yeah, because there's 3 digits here and there's 3 digits here. So our final answer is going to be 3 digits. Quinn, what was it that you were just saying? The velocity to the vector is west. Yeah. This is to the west. So you've either got to go 90 to the west, and then therefore 3.63 to the west, or what you could do is at the beginning of the problem define east as positive and make it negative 3.63, or you could have even defined west as positive and made it positive 3.63. But you got to indicate direction somehow because momentum is a vector. So it's a pretty straightforward question. But there's quite a few little things that could cause you to make a silly mistake, right? Like the unit conversions, the west, so on. Here's what I'm going to suggest you do always, all through Physics 30, to avoid making those silly mistakes. Okay? Take a pen that's a different color that you don't usually use, or a highlighter. Try to go to Staples or somewhere, some office supply store. Try to find the ugliest colored highlighter you can find that you'll never use for anything else, and use it for this one purpose. Every time we see a question, to circle things that can lead to silly mistakes, like grams, like kilometers per hour, that, like I'm telling you, those are unbelievably common mistakes, forgetting to convert from grams to kilometers per hour. And guess what? If you get a multiple choice question on an exam that's like this, guess what? If you forget to convert to kilometers per hour, you're going to get an answer that's there. You're going to think you have the right answer. And you're going to be surprised when you get your test back. I'd probably circle this as well, Quinn, just so I don't forget to either make it negative or write the word in, either way. Good? It's not that hard, is it? Ah. Man, Physics 30, listen, if the whole course is this easy, like we are set. We've got this aced. Okay, here's what I want to do with you right now. Since we've done one example, this is generally the way it will go. We do an example, give you a chance to do some work. So there's 4 questions on a worksheet that I'm going to put up on the board here right now that I want you to work on. These questions, if you want it on your phone in front of you, or if tonight you want to actually print off copies of the worksheets. Either way, whatever, I'll always put them up on the board, but you can always print off a hard copy yourself or bring them up on your phone if it's easier to do that, that's fine. You're going to find them under the About tab on Google Classroom. So when you go to Google Classroom, click the About tab, scroll to the bottom, and all the worksheets will be there for you. So right now, we're working on 1 to 4. Remember, P equals MV. Remember, red pen or ugly highlighter color, whatever you want to do, to circle or highlight all the things that can lead to silly mistakes. All right, let's take a look at our second example then. It's a little bit harder. Wouldn't say this is one of the hardest questions we'll do this year, but it's not one of the top 2 easiest questions we'll do this year either. A 1.5 kilogram object falls from rest from a height of 14.0 meters down to the ground level. We want to find the momentum of the object as it hits the ground. Listen, recognize that momentum exists at a specific moment in time. And we're talking about a time interval here. Like this object falls, right? So there's multiple moments in time. We want to find the momentum at that moment in time where it hits the ground. So in other words, we want to find the blank momentum. Final momentum, yeah. What do we need to find the final momentum? The initial, okay, is 0, right? 0 meters per second. What are we going to do with the initial velocity or the initial momentum in order to get the final momentum? Yeah, okay, it's accelerated. Yeah, yeah, we need a velocity, but the velocity is changing. It goes from 0 to something. We need the something. We need the final velocity. So let's write down a few givens here. We're going to say that our mass is 1.5 kilograms. We're going to say VI is 0 meters per second. We're going to say my displacement. You want to do that? Displacement is almost. I'm going to say my displacement is negative 14 meters. Cameron, why do you think I want to do that? Because it's going down, yeah. Or you could have said, I could have said HI is 14 meters, right? It's really the same thing. What's the momentum as it hits the ground? So we want to find PF. We know the mass is 1.5 kilograms. We don't know what VF is. Any ideas how we might find VF here? We have a data sheet, right? Look for I call it a relevant equation. Don't just look for a random equation that has VF in it. Look for a relevant equation, one that involves acceleration, but will also get us VF. Don't use V equals D over T, because that's for constant velocity, right? Everybody look back at that left side of your data sheet and see what you can find here. Cole says VF squared is equal to VI squared plus 2AD. Anybody else? Yeah, it looks like it fits, right? Let's say VF squared equals VI squared plus 2AD. What's A, by the way, Cole? Right, negative 9.81. So let's say VF is equal to 0 squared plus 2 times neg 9.81 times negative 14. And then let's remember to square root all that. And when we do that, what do we get here? 2 times 9.81 times 14. Square root that. You get 16.5735. And now we're there, right? What did we just find? What did we just calculate? No, we did not. But you're close. We did not find the final velocity. We found the final speed. We just found the final speed. Good, Alex. So what's the final velocity? Negative 16.5735, right? That equation doesn't get us velocity, it gets us speed. That's okay, because we know that it's moving downwards. We multiply that by 1.5, and we get 24.9. Actually, round it to 2 digits, it would be 25. I'm going to say negative 25 kilograms meters per second. Or you could have said 25. What else could you have said? Negative 25 or 25 downwards. Either one of those would work, right? So listen, same as the last question in a sense. We're looking for momentum, but we had to get velocity in order to solve for the momentum. And we just went back to our old acceleration equations for physics 20 to do that. You might think of another way we could have found final speed or velocity. Anybody try this? You guys remember that? Yeah, that would work, right? You just make your height, in this case, positive 14 instead of negative. Okay? Good? All right. Let's take a look at the next set of questions then, which is going to go questions 5 to 8 on that same worksheet. Question number 5 says a 5 kilogram ball accelerates, it should say from rest, at a rate of 2.00 meters per second squared for 1.5 seconds. Calculate the ball's momentum after the acceleration. Listen, there's no really, I don't think any red circle to do here, right? There's no strange units, there's no strange directions or so on. So we'll just go straight to writing down some givens. We know our mass is 5 kilograms. We know that VI, or we should have known that VI was 0 meters per second. We know that A is 2.00 meters per second squared. We know that delta T is 1.5 seconds. We're looking for PF again, the final momentum, right? Just like we were in our example. So we need VF, the final velocity. Like the velocity is changing, but we need the final. So how are we going to get it? How are we going to get it? We have A, we have VI, we have T. Let's go back to those equations. We have A, we have VI, and we have T. This is the list that we're allowed to try because those all involve acceleration. Which one is the one that we're going to do? We have A, we have VI, we have T. There is no wrong answer here, okay? What was A, by the way? 1.5? 1.2? Or just 2? Okay. And T was 1.5? And VI was 0. All of these are valid. You can try whichever one you want. You're not going to get the wrong answer. Let's go with this one. D is equal to VIT plus 1/2 AT squared. VI is 0 times T is 0 plus 1/2 of 2.0 times 1.5 squared. Look, that's going to give me a value of D. Is that what I'm looking for? No, I'm looking for VF. That's okay. That's not wrong, is it? I would just have to then sub it into an equation like this to solve for VF. So that's not the most efficient way to do this question, but it works. If you pick an equation that's valid and you get something out of it, great. Try something else to get what you're looking for out of it, right? Don't worry about being wrong. Just try something as long as you're trying something that's valid. What's the more efficient way of finding VF here rather than finding it this way? Yep. Yeah, probably that that equation right there, A is equal to delta V over delta T. Rearrange that. We get delta V is equal to A times T, which ends up being, I think it's 3 meters per second. VI is 0, delta V is 3. What's VF? 3, right? So now we just multiply the mass times 3, and we're good to go there. Does that make sense? Don't be afraid of these questions. Don't be afraid of trying something. Right? Just try something. Don't try random things, but try relevant things. And sooner or later, it's amazing how it just works out when you do that.